Hello everyone and welcome to this video on geometry. In the previous video we have discussed about angles, polygons and circles. So if you haven't watched that video, please go and watch that video before continuing with this one. In this video we will discuss about basic properties of quadrilaterals, parallelograms, rectangles, rhombus, square, trapezium and regular hexagon, and then finally we'll discuss the properties of circles. So let us first begin with quadrilaterals. So what is a quadrilateral? Any rectilinear figure with four sides is called as a quadrilateral. Quad means four, lateral means side. So any rectilinear figure with four sides is called a quadrilateral. So this is an example of a quadrilateral. Even a rectangle is a quadrilateral, a parallelogram is a quadrilateral, square, rhombus. These are all the examples of a quadrilateral. Okay. There are two formulas which will be applicable to all the quadrilaterals. Number one will be the formula for area of a quadrilateral. This is a general formula which you can use for any of the above mentioned quadrilaterals. For that, let us first of all join any of the two opposite vertices. Let's say if I join these two vertices. So now this is a diagonal. This diagonal is dividing this quadrilateral into two triangles, this upper triangle and this lower triangle. Now if I drop a perpendicular from this vertex to this diagonal, so if you notice, this will be the base and this will be the height of this triangle. Similarly, if I drop another perpendicular from this vertex to this base, so this part will be perpendicular to it. So for this triangle, this will be the base and this will be the height. Let's say the length of the diagonal is d, length of this height is h1 and length of this height is h2. So if we separately find the area of the two triangles and add them, we'll get the area of quadrilateral. So area of triangle, as we know, is given by half base into height. So for the upper triangle it will be half d into h1. For the lower triangle it will be half d into h2. We can take half d common, we'll get half d into h1 plus h2. So this area of quadrilateral you can use for any of the above mentioned quadrilaterals. Okay. Let us see now what is the second formula. If I join both the opposite vertices of the quadrilateral, say this one, this is one diagonal and this is the other diagonal, then as you can see the quadrilateral will be divided into four triangles, 1, 2, 3, 4. So let's say this area is A1, this area is A2, this is A3, this is A4. Then the product of the opposite areas will always be equal. So A1 into A2 will be equal to A3 into A4. Again, this formula is applicable for all of the above mentioned quadrilaterals. Now let us see what are the two different types of quadrilaterals. A cyclic quadrilateral and a tangential quadrilateral. If a quadrilateral is drawn in such a way that all the four vertices of the quadrilateral lies on the circumference of the circle, then such a quadrilateral is called as a cyclic quadrilateral. Okay. The most important property of a cyclic quadrilateral is that these opposite angles in a cyclic quadrilateral are supplementary. So let us name this quadrilateral A, B, C, D. So angle B plus angle D will be equal to 180 degree. Similarly, angle A plus angle C will also be equal to 180 degrees. So this is the first property that should come into your mind when you hear about the word cyclic quadrilateral. Okay, that the opposite angles are supplementary. In other words, their sum will be 180 degrees. The area of a cyclic quadrilateral is given by, let's say if length of this side is A, this side is B, this is C, this is D, then the area will be given by square root of s minus a into s minus b into s minus c into s minus d. Let us see now what is a tangential quadrilateral. If a quadrilateral is drawn in such a way that all the four sides of the quadrilateral are tangent to a circle, then such a quadrilateral is called as a tangential quadrilateral. Let us name this quadrilateral A, B, C, D. Then this point at which this side is tangent, let's call this E, this is F, this is G, this is H. Let the length of this side AB be equal to A, this entire thing BC be equal to B, DC be equal to C, and AD be equal to D. So these are the length. In tangential quadrilateral, the most important property is that sum of the opposite sides in a tangential quadrilateral will always be equal. So A plus C will be equal to B plus D. A plus C will be equal to B plus D. So how did we arrive at this relation? Let us understand that. First, let us consider a circle. If I draw two tangents from a point outside the circle, I have drawn two tangents from a common point which is outside the circle, then the length of these tangents will always be equal. We are going to use the same property and see how to arrive at this relation. If you consider these two tangents, FC and CG, they are drawn from a same common point C, hence their length will be equal. So this length will be equal to this length. Similarly, if we see at the tangent BE and BF, their length will also be equal. On the similar lines, AH will be equal to AE and DH will be equal to DG. Now if we take the sum of two opposite sides, let's say this will be AB plus CD. If we further break up AB and CD, it will be AE plus EB, AE plus EB or BE. Then CD can be written as GC plus GD. It will be GC plus GD. Now if we take the sum of the other two opposite sides, it will be AD plus BC. So we will have AD plus BC, which can be further written as AH plus HD plus BC. BC is BF plus FC. Now if you notice, what is AH? AH is same as AE, so we will replace AH by AE. What is HD? HD is same as BG, so we will replace HD by DG. And BF is same as BE, so BF is same as BE, and FC is same as GC, so we will have GC over here. Now if you look at these two equations, you will find that all the terms are same. We have AE here, we have GD here, we have a BE, GC and GC. From this we can say that equation 1 is equal to equation 2, therefore sum of the opposite sides in a tangential quadrilateral are equal. This is an important property, please keep this thing in mind. Now the area of a tangential quadrilateral is given by square root of A, B, C, D into sine of A plus C by 2, where A, B, C and D are the length of the sides of the quadrilateral, and here we have taken half of the sum of opposite angles. So in this case we have taken A and C, half of this, or you can also take half of B plus D. That will also do. Let us now move ahead and understand the concepts of parallelogram. So what is a parallelogram? A parallelogram is also a quadrilateral since it has four sides. Apart from that, in a parallelogram, the pair of opposite sides are parallel and equal. So this side is parallel to this side and their lengths are also equal. And this side is parallel to this side and their lengths are also equal. In addition to that, the opposite angles in a parallelogram are also equal. So if this angle is theta, this angle will also be theta. If this angle is beta, this angle will also be beta. Now, how do we find the area of a parallelogram? We can use that formula of half d into h1 plus h2 by drawing a diagonal and then dropping perpendicular to it. There is another formula that we can use. If we draw this diagonal, let's say join these two lines. So this is a diagonal. If you see, this diagonal will divide the parallelogram into two equal triangles. So if this length is A, this length will be A. If this length is B, this length will also be B. So as you can see, these are two triangles of equal areas because their sides are equal and we have two common angles as well. So as we know, the area of a triangle is given by product of the two sides and sine of the included angle. So it will be half into AB sine theta for this triangle, and for the above triangle also we'll have the same area, half AB into sine theta. This half and half will add up, we'll get A into B sine theta. So this will be the formula for area of a parallelogram. Now if you draw the second diagonal as well, then we'll notice that the diagonals of the parallelogram bisects each other. That means this length will be equal to this length and this length will be equal to this length. Okay. Now another important property of a parallelogram is that the adjacent angles in a parallelogram are supplementary. So theta plus beta will be equal to 180 degrees. Since they are lying between two parallel lines which are cut by a transversal, these will be co-interior angles and their sum will be equal to 180 degrees. Apart from these, all the properties that are applicable for a quadrilateral will also be applicable to a parallelogram. Let us now move ahead and understand what is a rectangle. Now a rectangle is a quadrilateral and it is a parallelogram as well. In this parallelogram, the opposite sides are parallel and their length is also equal. So this side and this side will also be parallel and equal. Apart from this, the adjacent angles are 90 degree. So this angle will be 90 degree, this angle will be 90 degree, this and this. All the angles in a rectangle will be 90 degrees. So all the properties that are applicable to parallelogram and quadrilateral will be also applicable to a rectangle. So let us say this length of this side is A and this side is B. So this will also be A and this will also be B. Area of a rectangle is given by base into height. So B is the base, A is the height. So area will be A into B. Perimeter will be 2 times A plus B. Let us now see what is a rhombus. Again, a rhombus is also a parallelogram with opposite sides parallel. So this side is parallel to this side is parallel to this side, and length of all these four sides will be equal. So length of all these four sides are equal, and the angle between two adjacent sides is not 90 degree. This angle can be anything but not 90 degree. Okay. So this is the basic definition of a rhombus. Let us see now how do we calculate the area of this rhombus. So if I draw one of the diagonal, so this diagonal will divide the rhombus into two triangles of equal areas, and if I draw the second diagonal as well, the diagonals will intersect each other at 90 degree and they will bisect each other. So this length will be equal to this length will be equal to this length. Let us name this rhombus A, B, C, D, and let this point be O. So area of the rhombus will be given by, let this be the length of the diagonal d1, and length of this diagonal be d2. So this part will be d2 by 2, and this part will be d2 by 2. Okay, so the area of the rhombus will be given by area of upper triangle plus area of the lower triangle, which will be half d1 into d2 by 2 plus half d1 into d2 by 2 for the lower triangle. From this we will get half d1 into d2. So this is the formula for area of a rhombus. Please remember that in a rhombus, length of all the four sides are equal and the adjacent angles are not 90 degrees. These are not 90 degrees. Okay, let's see now what is a square. A square is also a parallelogram. That means opposite sides are parallel, and in a square, length of all the sides are equal. In addition to that, the adjacent angles are 90 degrees. So all these angles are 90 degrees. As we have seen, in case of a parallelogram, opposite sides are parallel and equal. In case of a rectangle, opposite sides are parallel and equal, and the adjacent angle is equal to 90 degrees. In case of a rhombus, length of all the sides are equal, but the adjacent angle is not equal to 90 degrees. Whereas in case of square, length of all the sides are equal and the adjacent angles are also equal to 90 degrees. So this is the fine difference between rectangle, rhombus and square. Let us now see how do we calculate the area of a square. Now if we draw the diagonals of this square, it will also divide the square into two parts, two equal triangles. If we draw the second diagonal, the two diagonals will intersect each other at 90 degrees and they will bisect each other. So this length will be equal to this length will be equal to this length. If S is the side of the square, as we know, the area of the square will be given by S square. Perimeter of a square will be sum of all the sides. So S plus S plus S will be 4S. So this will be the perimeter. Now let us see what is the length of the diagonal. Since this side is S, this side is S, this is 90 degree. So we can apply the Pythagoras theorem. From this we will get the diagonal as square root 2 times S. So this will be the length of diagonal. Now two other important formulas are in radius and the circumradius. So let us see how do we calculate this. As you can see, in this square we have a circle which is inscribed in it, and there is another circle which is circumscribing it. So this is the circumcircle, its radius will be the circumradius, and this is the incircle, the radius of incircle will be in radius. Now if you see, this length is the diameter of the circle. This diameter of the circle is equal to the side of the square. So the radius of this circle will be half of side of the square. So the in radius will be R, which will be equal to half of the side of the square. And if we draw the diagonal of the circumcircle, we will see that it is same as the length of the diagonal. So the diameter, so the radius will be half of the length of the diagonal. So the circumradius is d by 2. D, as we know, is root 2 into S upon root 2 into S. D, as we know, is root 2 into S, and this thing when divided by 2 will become S by root 2. So this is the formula for the circumradius. Let us now move ahead. Trapezium. Now trapezium is simply a quadrilateral. It is not a parallelogram. It is a quadrilateral in which only one pair of opposite sides are parallel. So this side is parallel to this side. They are not equal in length. Their lengths will be different. And the other two sides will not be parallel to each other. So such a figure is called as a trapezium. What will be the area of trapezium? Let us name this figure A, B, C and D. Now if I drop a perpendicular from the vertex A to the base DC, then this will be the height of the trapezium, which is h. Area of a trapezium is given by half into sum of the parallel sides. So it will be AB plus CD. It will be AB plus CD multiplied by the height. So this is the formula for area of a trapezium. Now, if the length of the non-parallel sides, which is these two sides, if the length of the non-parallel sides are equal, if length of AD is equal to BC, then such a trapezium is called as an isosceles trapezium. In case of an isosceles trapezium, the length of the diagonals will be equal. So length AC will be equal to length BD. If you notice, these diagonals are lying between two parallel lines. Therefore, they will be divided into equal ratios. So let's say if this point is O, then if let's say AO is A, OC is B, OB is C and OD is D, then AO upon OC will be equal to OB upon OD. That is, A by B will be equal to C by D, and this entire thing will be equal to AB upon CD. So in case of an isosceles trapezium, this ratio holds true. Let us now consider the different areas in which the diagonals have divided the parallelogram. Let us name these areas. Let's call this as A1, this as A2, this as A3 and A4. If you observe the triangle ADC, this triangle ADC and the triangle DBC, both these triangles are lying between two parallel lines and they have a common base, which is DC. In such a case, if two triangles are lying between two parallel lines and have a common base, then their areas will be equal. So area of triangle ADC will be equal to area of triangle DBC. So what is area of triangle ABC? It is A1 plus A4. This will be equal to area of triangle DBC, which is A2 plus A4. So from here we'll get A1 equal to A2, as A4 on both the sides will cancel out. Now if we consider the triangles A3 and A2, if I drop a perpendicular from the point B to this diagonal, so this will be the height of the triangle AOB as well as BOC. So for area of triangle A3 will be given by half, base will be AO into height. Height will be B, let's say E. It will be BE. So this is the base and this is the height. Similarly, area of triangle A2 will be given by half. Here the base will be OC multiplied by the height, which is again BE. If we take the ratio of the two areas A3 upon A2, we'll get this half and half will cancel out, BE and BE will cancel out, which are the heights. So we'll get AO upon OC. What is AO? AO is A and OC is B. So the ratio of the areas A3 upon A2 will be A upon B. So this is also one of the important ratios. Now if you consider the triangle AOB, which is A3, and triangle DOC, whose area is A4. In this triangle you will observe these are the two parallel lines and we are forming a Z. So this angle will be equal to this angle. Then similarly, this angle will be equal to this angle. In addition to that, these are the two vertically opposite angles, AOB and DOC. So these two angles will also be equal. So we conclude that triangle AOB is similar to triangle DOC. So for two similar triangles, the ratio of their areas is given by, let's say, A3 upon A4 will be the area. It will be given by the ratio square of the ratio of the proportional side. So in this case, it will be, if we consider these two angles, angle B and angle D, side opposite to angle B is A, so A upon side opposite to angle D is B, so we'll get B and their square. So this is also one of the relations between the areas of the trapezium. So please remember these areas. I hope you are able to understand the logic between these relations and also this ratio. If you are able to remember these concepts, it will be sufficient for you to solving the problems based on trapezium. Let us now move ahead and understand the concept of regular hexagon. Now a hexagon is a six-sided figure. It's a regular hexagon, that means length of each side is equal. So this is how a hexagon look like. So this is how a hexagon looks like. If we join all the three major diagonals of a hexagon, then this hexagon will be divided into 6 equilateral triangles. 1, 2, 3, 4, 5, 6. If A is the side of this hexagon, then the side of each of these equilateral triangle will also be A. So the area of this hexagon will be given by 6 times area of an equilateral triangle, which is given by root 3 by 4 A square, which we can simplify it as 3 root 3 upon 2 A square. So this is the formula for area of a regular hexagon. In a regular hexagon, there are 3 major diagonals and 6 minor diagonals. So these ones in the blue are the major diagonals. Let's see which are the minor diagonals. If we join these two vertices, 1, 2, 3, 4, 5 and 6. So there are 6 minor diagonals and there are 3 major diagonals. Now what is the length of a minor diagonal? So the one in the green is a minor diagonal. If we consider this triangle, it is an equilateral triangle. The length of its side is A. So all of this side will be A. And this part represents the height of an equilateral triangle. So what is the formula for height? H will be root 3 by 2 A. This is the formula for height. So the length of the minor diagonal is nothing but H plus H, because this is also an equilateral triangle and all these triangles are concurrent. That means they have equal lengths. So the length of a minor diagonal will be 2 times H, which will be root 3 into A. For a major diagonal, so the ones in the blue were a major diagonal. So this is a major diagonal. Now, if you consider these two areas, these two triangles, one and the one which is below it, 2. This portion is the side of the triangle, its length is A. Even this portion is the side of the triangle whose length is A. So the length of the major diagonal will be equal to 2a. So please remember these formulas of area, number of major and minor diagonals, and their lengths. It will be helpful in solving problems. Let us now move ahead and understand circles. Let us consider this circle having center at O and radius r. The area of the circle is given by pi into r square. The perimeter is given by length of the circumference, which is 2 pi r. Now let us consider an arc ABC. So this arc ABC is called as a minor arc and the arc AC is called the major arc. Let us join the endpoints of this arc with the center of the circle, and the angle formed by this arc at the center of the circle, let this angle be theta. So this arc ABC is subtending an angle of theta at the center of the circle. Since this AO is the radius, so the length of the arc is given by r into theta, where theta you will have to enter in radians. If you are entering theta in degrees, then you will have to multiply it by pi by 180 degrees. Okay. Now this portion OABC, this entire thing is called as the sector. So OABC is called as the sector. How do we find the area of the sector? It will be half r into length of the arc, which is r theta. The theta is in radians. So we will finally get area of the sector as half r square into theta. If you are entering theta in degrees, you will have to multiply it by pi by 180 degrees. Now if I join this point AC, that is the endpoint of this arc AC, and drop a perpendicular from the center of the circle Now if I join the endpoints of this arc AC, what we will get is called as chord. So this length, this portion AC is called as the chord. So this is called as chord. Okay. Now if I drop a perpendicular from the center of the circle to the chord, then it will bisect the chord. That means length of this portion will be equal to length of this portion. Now if you notice this triangle AOCA, it is an isosceles triangle because the length of these two sides are equal. This is radius, this is also radius. Hence this angle and this angle will also be equal. In addition to that, we know the point at which the two equal sides of an isosceles triangle meets. If we draw a line perpendicular from that point to the opposite side, then it will bisect the angles. So this angle will be theta by 2 and this angle will also be theta by 2. Okay. We have to find what is the area of triangle OAC. OAC. Let us do that. By using the formula, we have area of triangle is equal to half into length of two sides and sine of the included angle. So this entire angle, which is theta, so we'll get area of triangle as half into r square into sine of theta. So this is the formula for area of triangle OAC. Now what is the length of the chord AC? For that, let this point be D. If we consider this triangle, AOD, in this, I'll just redraw the figure over here. So this is A, this is O, and this is D. This angle is 90 degree, this is R. And this angle was theta by 2. So in this triangle, if you apply sine theta by 2, sine theta by 2 is given by opposite, which is AD, upon the hypotenuse, which is r. So what is AD? AD will be equal to r into sine theta by 2. Now what is the length of the chord AC? AC is 2 times AD because this part and this part are equal. So length of the chord AC will be equal to 2 times length of AD, which is r sine theta by 2. So length of chord AC will be 2r sine theta by 2. Now what is a segment? First of all, understand what is the segment. We have seen this entire part was called as sector. This entire part was a sector. This portion is called as the arc of the circle, and this portion is the chord of the circle. The portion between the arc and the chord of the circle is called as the segment. So this lower portion is called as the segment of a circle. This is the minor segment, and this upper portion will be major segment. What we have been asked to find is what is the area of the segment DABC. So DABC, what will be the area? This will be equal to area of the sector, which was the entire yellowish thing, minus area of the triangle OAC. If we subtract area of triangle from the area of sector, we will get the area of segment. What will be the perimeter of segment? So the perimeter will be length of the chord plus length of the arc. Length of the chord plus length of the arc. So I hope you are able to understand all these formulas, how they are arrived at, and the basic concepts of sectors, chords and segments. Let us now move ahead and understand some of the basic properties related to a circle. Now the first property is related to an angle. The angles subtended by an arc in the same segment are always equal. So let's consider this arc AB, and let this be the center of the circle O. So here we will have, if I join these two endpoints of the arc, we will have the two segments. This is the lower segment and this is the upper segment. So the angle subtended by this arc AB in the upper segment at anywhere in the upper segment, whether here, here or even here, all these angles will always be equal. If this is theta, this angle will also be theta and this angle will also be theta. Then the second property, angle subtended by an arc at the center of the circle is twice the corresponding vertical angle. So this is the arc. If we joined it with the center of the circle, so this will be the angle that is subtended by the arc at the center of the circle. It will be twice the corresponding vertical angle. So what will be the vertical angle? It will be this angle, which is theta. So if this angle is theta, this angle will be 2 theta. Okay. Let us now see some properties related to chords. Chords which are equidistant from the center of the circle are of equal length. So if these two chords are at an equal distance, x and x, then their length will also be equal. So the length of this chord will be equal to the length of this chord. Conversely, if the length of two chords of a circle are equal, then they will be at equal distance from the center of the circle. Okay. Let us now consider the second property of chords is the common chords of congruent circle are equidistant from center of the circle and subtend equal angle at the centers. So these two circles are congruent. What do you mean by congruent circles? Their radius will be equal. So if its radius is r, the radius of this circle will also be r. and this chord which is drawn in the overlapping portion is called as the common chord. So this common chord will be at equal distance from the center of both the circles. So if this chord is at a distance of x from this circle, it will also be at a distance of x from the second circle. Also, the angle subtended by this chord at the center of the circles will also be equal. So angle subtended by this chord on the center of this circle, if this is theta, then the angle subtended by this chord on the other circle will also be theta. Let us now understand the most important formula from the point of view of circles, the alternate segment theorem. Let us consider this figure. This is the tangent to the circle at, let's say, point A, and this portion is the chord of the circle, let's say AB. If AB is the chord of the circle and AC is the tangent to the circle, then the angle subtended by the chord with the tangent, which is this angle theta, it will be same as the angle subtended by the chord in the opposite segment. So the angle subtended by the chord in the opposite segment will be, let's say, this angle. So this angle will also be theta. Please understand this. The angle subtended by a chord with the tangent, which is this angle, it will be same as the angle subtended by the chord in the opposite segment. So in the opposite segment, that means anywhere on this segment. You can take it here also. So if this angle is theta, this angle will also be theta. You can take it here also. This angle will also be theta. This is a very important concept which will be helpful in solving a lot of problems based on circles. Let us now understand what is tangent secant theorem and secant secant theorem. First of all, let us understand what is a secant. A tangent touches the circle at only one point, whereas a secant, it intersects the circle at 2 points. So any line that intersects the circle at 2 points is called as a secant. So this portion, this line is called as a secant. Let's call this as A, B, C and D. So as per tangent secant theorem, length of the tangent, square of the length of the tangent will be equal to AC into AB. There is another formula which is called secant secant theorem. In this we will have two seconds. Let's call this point as P and name them A, P, C, D. So as per secant secant theorem, PA into PB will be equal to PC into PD, PC into PD. So these are also two useful formulas which will be helpful in solving problems. Please remember them. Let us now understand how to calculate the length of tangents. There are two types of tangents, direct common tangent and transverse common tangent. We'll understand what is the difference between direct common tangent and transverse common tangent in a short while. Let us first name this figure. As you can see, there are two circles. Let the radius of this circle be R1 and the radius of this circle be R2, where R2 is greater than R1. Okay. This line is the direct common tangent. This line in red color is the line which is joining the center of the two circles. So this is line joining the center. The ones in the yellow are the radial lines. The radial line are always perpendicular to the tangents. So this angle and this angle will be 90 degrees. Now let the length of the direct common tangent be L and the distance between the center be C. So this length will be C and this length will be L. Now if you take a line which is parallel to this direct common tangent and just bring it over here, so the length of this line will also be equal to L. Now since this is the radial line and this line is parallel to this line, hence if this angle is 90, this angle will also be 90. This length is L, this red length is C. Now this is R1, this portion, and this portion from here to here is parallel to this line. So if this is R1, this portion from here to here will also be R1. This entire thing is the radius of this circle, which is R2. So just this portion will be R2 minus R1. So now if you consider this triangle, let's say OAB, in this triangle OAB, angle ABO is 90 degree. So if you apply the Pythagoras theorem, from this we'll get square of the hypotenuse, which will be C square will be equal to L square plus R2 minus R1 the whole square. So we'll have L square plus R2 minus R1 the whole square. So from here we'll get L square is equal to C square minus R2 minus R1 the whole square. So from here we'll get L will be equal to square root of C minus R2 minus R1 the whole square. So this is the formula for length of a direct common tangent. Now let us see how do we calculate the length of transverse common tangent. Let us name this figure. This is a circle of radius R1. This is a circle of radius R2, where R2 is greater than R1. This red line is the line which is joining the center of the two circles. So let this length be equal to C. Now if you see this blue line, this is the transverse common tangent. So what is the difference between transverse common tangent and direct common tangent? If you observe the direct common tangent, the tangent line is not intersecting or not cutting the line joining the center. Whereas in transverse common tangent, you will see the tangent line is intersecting or cutting the line which is joining the center of the two circles. So any tangent which cuts the line joining the center of the circle is called as transverse common tangent, and any tangent which does not cut the line joining the center of the circle is called as the direct common tangent. Okay, I hope the difference is clear now. Let us calculate further. So if I draw a line which is parallel to this tangent, we'll get this line. So if the length of this tangent is L, so length of this line will also be equal to L. Now this radius is R2, this radius from here to here is R1. This line we have just extended here, so this line is parallel to this line. So if this length is R2, this length will be R2 as well. Now this is the radial line, this is the tangent line. So radius line is always perpendicular to the tangent line. So this angle will be 90 degree. If this angle is 90 degree, this angle will also be 90 degree. Now if we consider the triangle A, B, C, in this triangle we'll see that, I'll just redraw the figure over here. This is A, this is B, this is C, and this angle ACB is 90 degree. This portion is R1 plus R2. This portion is equal to length of the tangent, and this AB is the length of the line joining the center of the circle. Again, if we apply the Pythagoras theorem, we'll get C square is equal to R1 plus R2 the whole square plus L square. So from here we'll get L square is equal to C square minus R1 plus R2 the whole square. If we take the square root, the length of the transverse common tangent will be given by square root of C square minus R1 plus R2 the whole square. So this is the formula for transverse common tangent. If you notice, the formula for direct common tangent and transverse common tangent are almost the same. We'll end this session over here. In the next video, we will solve problems based on these formulas that we have learned in the part 1 and part 2 of this video. Thank you.